After studying this module, you shall be able to know the various selection rules involved for the transitions. You will also learn about the various factors involved in the breakdown of the selection rules. You will identify various aspects of the absorption and emission spectrum. You will analyze the transition probability of the complexes. Spectrum in general for various species, that is compounds, complexes and elements, can be correlated in the following two ways. The first is the absorption spectrum. This type of spectrum is obtained when absorption of the radiation occurs by the molecule, atom or the absorbing species, which leads to the transition of the electrons from the lower to the higher level. The other one is emission spectrum. This is just the reverse of the absorption spectrum, in which the transition from the higher to the lower level occurs due to the emission of radiation by electrons to the radiation field. In this case, no radiation is observed, then the transition from higher to lower level is termed as non-radiative decay.
Firstly, we are going to discuss what is an emission spectrum. The emission spectrum can be of namely three types. First, continuous spectrum, second, band spectrum, and third, line spectrum. We are going to discuss each one of them one by one. First of all, what is a continuous spectra? The continuous spectrum for a substance is obtained when the molecules of the substance are thermally excited by providing large amount of heat. For example, when solids such as iron, aluminium, carbon are heated up to the extent that they start blazing. It is the spectrum of electromagnetic waves that involves a wide range of the wavelengths. In the visible portion of electromagnetic spectrum, a continuous spectrum would look like a rainbow. It has been depicted, which shows the spectrum of a common incandescent light bulbs, which spans all visible wavelengths without interruption. Next, we are going to discuss a band spectrum. When the thermal excitation given to the molecules of a substance is not enough to lead to a continuous spectrum, we get a band type of a spectrum. In this case, we get spectrum in the form of huge number of bands different in color. Basically, the spectrum consists of a large number of closely spaced lines which appear to give a look of different colored bands. The spectrum is sharp at one end which fades away at the other end. This sharp end is called the head, whereas the faded region is called the tail. This kind of spectrum has been shown in figure 3, which shows the band emission spectrum for the nitrogen gas. Next, we are going to discuss the line spectrum. The line spectrum is given by the elements in their vapor form. It consists of lines at the different intervals of the spectrum against dark background. The intensity of lines is mostly different from each other. The molecular and electronic arrangement of the elements leads to this type of line spectrum. Hence, two elements cannot have same type of the line spectrum, which shows low density cloud of gas emitting light only at specific wavelengths that depend on its composition and temperature, which produces a spectrum with bright emission lines. Next, we are going to discuss the absorption spectrum. In order to have the absorption spectrum, the sample has to be placed between a light source and the spectrum recorder, which measures the amount, intensity, and frequency of the light absorbed by the sample. The part of the spectrum absorbed by the sample hence correlates to the absorption spectrum of the sample. The electronic absorption spectrum for the transition metal complexes are of two types, namely DT transition spectrum and charge transfer transition spectrum. As the name suggests, in the case of DD spectrum, the transition occurs within the d orbitals, and in the case of charge transfer spectrum, the transitions takes place from ligand to the metal or from the metal to the ligand. Figure 5 shows the basic absorption spectrophotometer and its working, where we have a light source, monochromator, a sample which has to be placed, and the detector with help of which the absorption spectrometer is recording a spectrum. Next, we are going to discuss the electronic spectra of transition metal complexes. Next, we have to discuss the various principles governing the transitions occurring between various electronic levels in the transition metal complexes. Some of these principles have been discussed below. Firstly, we have to discuss the Franck-Cordon principle. The time taken by the electronic transition is quite small, of the order of 10 raised to the power minus 15 seconds, and thus the molecule or the atom undergoing transition does not have enough time to appreciably change its position or the configuration. Because of this, it can be said the vibrational kinetic energy of the species undergoing transition will be same in the excited as well as the ground state. Also, an alternate statement can be said that since the movement of the nuclei during the course of transition is negligible, the internuclear distances do not change, and most probable transitions will be those which occur vertically. The Franck-Cordon principle. Next, we are going to discuss the electronic transitions occurring between transition states. Quite often, transitions arise from the ground vibrational level of the ground electronic state to several other vibrational levels of potential excited electronic states. These transitions give rise to vibrational fine structure in the foremost peak of the electronic transition. Since all the molecules are present in the ground vibrational level, nearly all transitions that give peak in the absorption spectrum will arise from the ground electronic state. If the different excited vibrational levels are represented as mu1, mu2, etc., and the ground state is shown as mu0, the fine structure in the main peak of the spectrum is assigned to mu0 to mu1, mu0 to mu2, mu0 to mu3, etc. The mu0 to mu0 transition is of lowest energy and longest wavelength transition. The basic absorption spectrum which gets vibrational fine structure when it is resolved. Next, we are going to discuss the transition probability. For the absorption spectrum to appear, light must be absorbed by the molecule. Light will be absorbed if it can interact with the molecule by its oscillating electric and magnetic fields. For this to take place, the dipole moment of the molecule must change during the time of the transition. If the change in dipole moment is quite large, number of photons will be absorbed, which further leads to intense bands of larger area. Otherwise, small change in the dipole moment would lead to less absorption of photons and hence lesser area and weak absorption bands of low intensity. Figure 8 depicts the vibrations that can lead to a change in the dipole moment. These can be A1G symmetry vibration and T1U symmetry vibrations. The probability of transition is directly proportional to the transition momentum mu. Psi1 is the initial state, Psi-f is the final state, mu is the electric dipole moment operator. Then the transition moment probability can be defined in terms of initial state, final state, and their component in the electric dipole moment operator. The intensity of absorption will be directly proportional to the square of transition moment probability. The transition will be allowed if the value is not equal to 0, and it will be forbidden if the value is going to be equal to 0. Next, we are going to discuss the various selection rules and how their breakdown takes place. The various selection rules that govern the feasibility of a transition for transition metal complexes are given below. Lipot selection rule. This rule states that for a molecule having center of symmetry, transitions within the same subshell are forbidden. As per this rule, the PP or DD transitions are forbidden. Mathematically, the rule can be stated in the form of an equation, that is, for any transition to take place, change in the value of total orbital angular momentum between the final and initial state should be delta L should be equal to plus minus 1, where delta L is equal to LF, that is the total angular momentum of the final state, subtracted by Li, the total angular momentum of the initial state. The transitions occurring between the states of same parity are disallowed, which means the d orbitals which are gyrate in terms of parity or symmetric with respect to the center of inversion cannot have transitions from one d orbital to the other. However, p orbitals are ungyrate, that are asymmetric with respect to the center of inversion, and thus transition can take place between d and p orbitals. In very simple words, d-d transitions as well as p-p transitions are not allowed, whereas p to d and d to p transitions are allowed. According to the next rule, in case of states with different spin multiplicity, the transitions cannot occur. The spin multiplicity value is given by 2s plus 1. Thus, transitions between 1d1 and 1a1 are allowed in terms of spin multiplicity, whereas between triplet d1 and 4a2 are not. The transitions which are feasible are called spin allowed, whereas those with the different spins are termed as spin forbidden. The value of delta S should be equal to 0. In case these rules are completely followed by the transition metal complexes, many of the transition must have not been observed. But actually, these transitions occur, which suggests that we can have cases where these values are broken down to actually display the forbidden transitions. Next, we are going to discuss the breakdown of the selection rules. There are various phenomena that can lead to the breakdown of the selection rules mentioned above. These are explained as follows. During the course of vibrations in a transition metal complex, which is flexible in terms of movement about the bonds, the orbitals present can temporarily lose their center of symmetry. Since the parity is lost for the movement, it can be said that vibranic coupling results in the loss of their symmetric identity, due to which the transitions from d to d orbitals are partly allowed. Although these transitions are observed, but their molar extinction coefficient is extremely low, of the order of 10 to 50 liters per mole per centimeter. These transitions are actually responsible for the various colors of the transition metal complexes. Next, the tetrahedral complexes have no center of symmetry, and thus they are not gyrate in symmetric terms. Thus, the D levels in them are E and T2 with no G as subscript. In case of a metal sigma bonding, the hybridizations sp3 as well as sd3 both are sustainable, and thus the p and d orbitals present are not pure but mixed in nature. Because of this D and P mixing, the Laporte selection rule is relaxed. Hence, tetrahedral complexes are often more intensely colored in comparison to their octahedral counterparts. This is actually a consequence of Laporte relaxation. The spin orbital coupling in case of certain complexes leads to the relaxation of spin selection rule. For metal ions, mostly 4d and 5d, spin orbit coupling is quite strong, and thus in these complexes the spin multiplicity rule is relaxed to a good extent that results in the occurrence of the forbidden transitions.
Absorption spectrum is obtained when absorption of radiation occurs by the absorbing species, which leads to the transition of the electrons from the lower to the higher level. Emission spectrum is obtained by transition from higher to the lower level that occurs due to emission of radiation by the electrons to the radiation field. Emission spectra are of namely three types. First is continuous spectra, second is band spectra, and third is the line spectra. Frank-Cordon principle states that movement of the nuclei during the course of transition is negligible, and thus it can be said that internuclear distances do not alter during the course of the transition, and the most probable transitions are those which occur vertically. Transitions arise from the ground vibrational level of the ground electronic state to several different vibrational levels of potential excited electronic states. These transitions give rise to vibrational fine structure in the foremost peak of the electronic transition. Light will be absorbed if it can interact with the molecule by its oscillating electric and magnetic fields. For this to take place, the dipole moment of the molecule must change during the time of transition. If the change in the dipole moment is quite large, more number of the photons will be absorbed, which further leads to intense band of the larger area. Lepard's selection rule states that for the molecules having center of symmetry, the transitions within the same subshell are forbidden. In cases of states with same spin multiplicity, the transitions cannot occur. The spin multiplicity will be represented by the formula 2s plus 1. During the course of vibrations in the transition metal complex, which is flexible in terms of movement about the bonds, the orbitals present can temporarily lose their center of symmetry. Since the parity is lost for the moment, the vibrionic coupling results in the loss of their symmetry, and it is identified due to which the transitions from d to d orbitals will then become allowed. Tetrahedral complexes are often more intensely colored in comparison to their octahedral counterpart, and this is due to the dp mixing. For metal ions, mostly 4d and 5d spin orbit coupling is quite strong, and thus in their complexes the spin multiplicity rule is relaxed to a good extent, which will result in the occurrence of the forbidden transitions.